Hello friends, welcome to the NPTEL certification course on welding of advanced size and steel for automotive applications. My name is Murugan Amirthalingam. I am working in the Department of Metallurgical Materials Engineering in the Indian Institute of Technology, Madras. In the next 4 weeks, I am going to talk about the welding behavior of the modern automotive steels. So I hope you enjoy attending this course. And yeah, you are most welcome to ask any questions if you have during this course in the forum, as well as you can contact me through the NPTEL website. You must have also seen me in the introduction video. I hope you attend this course with keen interest and learn about these advanced size and steels and the welding behavior of these steels. Okay, before going into details, I request all of you to do the assignment 0. I hope you must have done it. So make sure that you score minimum of 6 out of 10 I asked, because that is very important to judge yourself whether you are capable of attending this course and understanding the concept that I am going to explain during these 4 weeks. Even if you don't score 6 marks, it doesn't matter. You can still go through the subjects what I'm going to describe in the introduction video, what I described in the introduction video, and what I'm going to talk about now for next half an hour or so. So you brush up your basic, and then you can also ask me if you need any help in terms of literatures or reference books or any materials which can make you comfortable attending this course. Okay, so having said that, you can refer following these textbooks for your course, for your reference. So you can refer one of my books, the Microstructure development during welding of strip steels. So you can freely download this book from the repository of library.udelf.nl. So the chapters I am going to talk about in introduction to advanced size and steels, the basic and the welding metallurgy of advanced size and steels are all covered in the textbook. Please refer to that book, and plus I'll be giving out the handouts and the slides what I'm going to show you during the course of these lectures. So you can refer that, and of course, and you can also ask any questions if you have during this course through the forum. I'll be glad to answer all the questions. Some of the literatures I am going to use for these lectures actually from the ULSAB documentation. So what is ULSAB? ULSAB is ultralight steel auto body, the advanced vehicle concepts. It is actually a body set up by the steel and automakers. So you can download the various reports, the materials what I am going to refer from the website www.worldautosteel.org. It's a very nice website, and you can go and learn a lot about the advanced size and steels as well as their processing and the applications. So I am also going to teach some fundamentals about the steel physical metallurgy, which is very important, because your fundamentals of welding metallurgy of advanced size and steels are all from the physical metallurgy, the heat treatment, the effect of thermal cycles of the welding process on the phase transformations. Okay, so those I'll be teaching anyway during the first introduction hour. And you can also refer the fundamentals of materials and engineering by William Callister book, which is also very handy. Okay, so apart from that, I'll also be giving these slides and some of the literatures of my own for your reference. Good. So this slide shows the overview of the course content, right? So the first unit, I'll be giving introduction about steel physical metallurgy. So basics, fundamentals about iron carbon system, and also what is a microstructure for a given composition. What are the microstructural phases you may expect for a given heat treatment, for example in a weld thermal cycle in particular. And then I'll move on to the introduction about the advanced size and steels. So why do we need these steels, and what makes them interesting for automotive applications. So what is the driving force for development of these steels, and what are the advantages in terms of economy, in terms of cost, in terms of environment, what are the advantages we are going to gain by replacing the conventionally used steels with the advanced steels in auto bodies. Okay. Then I will move on to the introduction to various welding processes that are commonly used in automotive industries to weld steels and other alloys. I will concentrate on some of the interesting and important 3 welding processes: the advanced gas metal arc welding process, and resistance spot welding process, and the third and finally laser welding processes. I will give you introduction about all these 3 processes, what are the important process parameters, those dictate the weldability and the final mechanical properties of the weld, and how we can favorably modify those welding parameters to achieve better microstructures and good mechanical properties. In the second unit, in third week, so I will be moving towards the actual welding metallurgy of advanced resistance steels. So I will talk about the effect of weld thermal cycles on the various microstructural development, stability of phases that are generally present in these steels, and what are the roles of alloying elements that we add. For example, we add carbon, manganese, silicon, aluminum, in some cases even some amount of boron, and some of the impurities like phosphorus, sulfur, they are always present. And what are the roles of the alloying elements during the development of microstructure while applying the weld thermal cycle. And so there are some interesting phenomena that are happening while welding of advanced resistance steels, such as the segregation, microsegregation, and the hot cracking during welding. These are all interesting topics and important topics you need to understand to understand the welding behavior of advanced resistance steels. And the final week, then we will move on to the mechanical properties of the advanced resistance steel weldments. So we will start with an introduction to the common testing methodology that are used in to evaluate the mechanical performance of welds in automotive industries. For example, we will see tensile shear testing and for example cross tension testing, and see what are the standards that are actually used to govern the testing methodology of evaluating the mechanical properties of the weldments. And then we will move on to the effect of microstructural changes that are happening in the heat affected zone on the mechanical properties, such as change softening that is commonly observed in some advanced resistance steels. And we will look at how the weld thermal cycles can favorably modified to achieve good mechanical properties. So we will see the effect of the common weld thermal cycles, as well as we can also modify the general weld thermal cycles to achieve good mechanical properties. For example, use of post pulsing and post weld heat treatments to get the desirable microstructure in the fusion as well as the heat affected zone. So this gives the overview of the actual the course which I am going to take for next 4 weeks. So I will try to make it as easy as possible. I know most of the students who are attending this course are all not from metallurgical background. It does not matter even if you are from mechanical sciences or any other background. I will make it as simple as possible, and I hope you enjoy attending this course. So before going into the detail about advanced resistance steel, the first thing you need to understand is the steel physical metallurgy, because that is very important in order to cope yourself for the subsequent topics. Okay, so I will just give you the basic introduction about the steel physical metallurgy. So steel, you all know that it is an alloy of iron and carbon. Okay, so we add carbon into iron. Apart from carbon, we also add other alloying elements. Various alloying elements is possible. The most common are manganese, silicon, chromium, nickel, and other alloying elements which are added to improve various performances, mechanical performances, like niobium, titanium, vanadium. These are all micro alloying additions to cause precipitates, or some special alloying elements. Sometimes we even add boron. Apart from these alloying elements, we also have impurities. Generally, phosphorus and sulfur, they are all considered impurities. It's very difficult to remove them, so we'll have to work with them. Even though if they are there in a trace amount, they may still cause various problems during welding. So we look at the effect of alloying elements and the role of heat treatment and the role of both combination of alloying elements and heat treatment on the microstructural generation. Okay, so we'll go one by one, first to understand the fundamentals of iron carbon system. Okay, so if you look at the moment you say the iron carbon system, we look at phase diagrams. Okay, so I hope all of you are familiar with the iron carbon phase diagram. If you are not, I am going to show you now the iron carbon phase diagram. What you see over here, various lines, which each line actually means a lot in this phase diagram. If you look at the axes, what we have it here is the temperature axis in y axis and the composition in x axis. The composition generally, because this is a pure iron carbon diagram, so we have the composition in x axis, which is actually carbon, and the temperature is in y axis. The moment you say steel, we restrict the composition of the carbon less than the 2.14. So the carbon concentration is less than 2.14 is considered steel. The reason is the solidification behavior, what you see over here, which I am not going to into detail, so you can refer some textbooks about it. So what is interesting in this here in this course perspective is the regions that are present, the temperature ranges of 1000 degrees centigrade, maximum carbon concentration of 1%. Okay, this region, what you see over here, is known as the eutectoid region of the phase diagram. So eutectoid is, okay, it's nothing but we have here a transformation of austenite, which is an FCC phase, the high temperature, the allotropic phase of the iron, is transforming into the mixture of the what you call the ferrite and the cementite. Okay, and this happens 100%. That means that austenite transform to pure ferrite plus cementite mixture at the carbon concentration of 0.76. So this is the eutectoid carbon concentration. It's very important. In this course, as I said, we will be looking at advanced ice and steels. Generally, the advanced ice and steel, the carbon concentration vary somewhere from say 0.05 to not more than 0.258%. So our carbon concentration range, so in this steel, advanced ice and steel generally lie somewhere over these regions. Okay, and what you see over here in this region is the lines corresponding to the carbon concentration in various phases, right. So if you look at this line over here, so this line indicate the carbon concentration in ferrite, which is in equilibrium with austenite, and this line indicates the carbon concentration of austenite, which is in equilibrium with ferrite. So that you should be understanding clearly. So this line indicates the carbon concentration of ferrite, which is in equilibrium with austenite. Okay. So if you look at it, these two lines, your carbon concentration of austenite decreases with decreasing temperature. Similarly, you have a line which indicates the carbon concentration of ferrite, which is in equilibrium with austenite, which is also slightly decreasing but not as significant as the other line. and this point corresponds to the eutectoid composition, where the austenite can completely transform into the mixture of ferrite and cementite, and this mixture is known as pearlite, right. And we will see how the microstructure of pearlite looks like in subsequent slides. So, in this slide it should be clear that the carbon concentration of advanced and steels, which are of interest to us, it actually ranges from 0 to say about say 0.25 weight%, right. So, now if you look at this diagram, so if you heat up a steel containing say 0.2 weight% carbon to higher temperatures, okay, and whatever microstructure you have would transform to austenite the moment your temperature reaches at this temperature. When you heat it up, your entire microstructure would transform into austenite under equilibrium conditions. So, if you are heating up above, say for example, in this case 820 degrees centigrade in a pure iron carbon system, you expect your microstructure fully transforming into the austenite. Okay. So, if you are heating up the microstructure containing 0.2 weight% carbon of a pure iron carbon system, the moment the temperature reaches above say 820 degrees centigrade, you will form a complete austenitic microstructure. Okay. When you cool down subsequently to room temperature, okay, based on the cooling rate, you would end up forming the microstructure which can have a mixture of ferrite, pearlite, or the other variants of pearlitic structures such as Bainite, or even if you cool very rapidly, you may end up forming Martensite. Okay. So, first you need to understand from this graph is, so suppose if you have a 0.2 weight% carbon and you are cooling down to room temperature, your austenite would keep on enriching because of the formation of first the ferrite, and then subsequently the moment the austenite which is untransformed reaches the carbon concentration of eutectoid carbon concentration, then you will end up forming pearlite. Okay. Now, whatever the ferrite that formed before the pearlitic reaction is known as the pro-eutectoid ferrite, because it is actually forming before the eutectoid reaction. So, that is known as pro-eutectoid ferrite. And subsequently, the moment the carbon concentration of austenite reaches the eutectoid carbon concentration, the remaining austenite would transform into pearlite. Okay. So, if you are cooling steel containing 0.2 weight% carbon, you may have a mixture of pro-eutectoid ferrite and pearlite, right. So, now this diagram does not tell you about the time. Okay. So, what are the effect of cooling rates and what are the effects of alloying elements, because apart from carbon we also have various alloying elements that are actually added. So, based on the concentration of all other alloying elements and cooling rates, the nature, the morphology of the phases that are forming from austenite can also change, right. So, now we look at in detail first what are the forming mechanism of pearlite from the austenite when you are cooling down at various compositions, and we will move on to the effect of alloying elements on the transformations, and subsequently we will go to see the effect of cooling rates or the time in the time variant, the time factor in this phase in these transformations. So, I already explained that the 0.76% carbon, which is your eutectoid carbon concentration. So, suppose if you start with the steel, it is not advanced size and steel, a steel containing say 0.7% weight% carbon. So, if you are cooling this steel containing this carbon, so obviously the transformation of austenite would be completely to Pearlitic transformations, where you would expect the mixture of ferrite and cementite forming. Okay, so what you see over here, the ferrite and cementite will be forming in a lamellar manner. We will see in subsequent slides how exactly the formation mechanism of Pearlite for this eutectide composition steel. So, this composition, as already explained, is known as eutectide composition. This generally happens in iron carbon pure iron carbon system at 0.76 carbon weight percent carbon. If you add alloying elements, you would also change the eutectide compositions based on the nature of alloying elements. We will discuss about it also in later. Suppose, as I already explained, our advanced sites and steels contain the carbon concentration in between around say 0.05 to 0.25 weight percent, right. Then the steel composition lies in this region. Okay. So, we define the steel composition that are actually less than the eutectide composition is known as the hypoeutectoid steels, because the carbon concentration is less than eutectide point. Okay, hypoeutectoid steels. The steels that are having the carbon concentration above the eutectide point, they are known as hypereutectoid steels. Right. So, our advanced sites and steels are all hypoeutectoid steels, where the carbon concentration is less than eutectide composition, right. So, as I already explained in previous slide, our composition lies somewhere over here, right. So, now imagine we have the composition something about 0.25 weight percent. If you go and look at the transformation mechanism, as already explained in previous slides. So, we have the austenite, which is a phase-nut cubic structure. So, when you cool it to subsequent temperatures, the moment your temperature reaches below this line, you would start nucleating ferrite based on your cooling rate. Okay. Suppose if you are cooling to a temperature below temperature of say, which is actually known as an A3 temperature. So, you would start nucleating ferrite. So, the moment you start nucleating ferrite, what happens? The carbon concentration of ferrite, as I already explained, is actually given by this line, right. So, this is your carbon concentration of ferrite, and this is your austenite carbon concentration. If you subsequently cool further, your ferrite would start growing in the austenite matrix. In this case, this is ferrite, and during this process, the carbon would start be going out of ferrite into austenite and segregating the austenite, and your carbon concentration austenite would change according to this line. The moment your austenite carbon concentration reaches this point, you would trigger the Pearlitic transformation. It is nothing but mixture of ferrite and cementite. Good. Now, if you look at the actual microstructure of the steels, the both steels I talked about, the steels containing 0.76%, close to eutectide carbon concentration, you will have 100% Pearlite, because there is no other transformation. The entire austenite will be transforming into Pearlite, and the microstructure looks like what you call it, is a fingerprint of your finger, where you see lamellars of here is black is cementite and this is ferrite. If the steel contains the carbon concentration less than eutectide concentration, your microstructure contains first the ferrite, which is pro-eutectoid ferrite, and upon sufficient enrichment in carbon, the austenite would transform into eutectide Pearlite. So, this is eutectoid Pearlite. Okay. So, a condition for this is your carbon concentration must be less than eutectide composition, which is 0.76, and most of our advanced sites and steels composition would lie in this composition range, where if you are cooling sufficiently slow, you would end up forming ferrite plus pearlite, which is nothing but mixture of ferrite and cementite. Right, it's clear? Good. So now, as I already explained, the iron carbon phase diagram does not consider the time effect, right. So we need to incorporate the time effect in the to understand the phase transformations, the kinetics of phase transformation, how fast the reaction can take place in whether holding at some temperatures or subsequently cooling to room temperature continuously from austenitic temperatures. Okay. So we use two types of diagrams to understand the phase transformations in iron carbon systems. The first diagram I am going to talk about is the time temperature transformation diagrams. Okay. And in this diagram is used to describe the phase transformation kinetics when you are holding isothermally at a temperature upon cooling from the austenitizen temperature. Say this diagram shows the time temperature transformation diagrams, where we plot the various curves which I am going to explain in two axes, on y axis temperature and x axis the time of holding in this case. So this diagram can explain, say for example, if you are cooling from the fully austenitic region rapidly and then hold it a particular temperature, and we can identify the start and end of transformation. Okay. So at what time your transformation from austenite to pearlite begins and your austenite to pearlite ends, right. And so we can cool it to various temperatures and hold it and identify the start of transformation and end of transformation. So this is start of transformation and this is end of transformation. Okay. But in this diagram, so the commercial application of this diagram is limited, because in most of the applications, for example in welding, our transformation is happening under continuous cooling, right. So the sample is cooled continuously from austenitic temperature to room temperatures. So we need to include the other parameters compared to this diagram, which is known as continuous cooling transformation diagrams. Okay. So in the continuous cooling transformation diagrams, where we identify the start and end of transformation when you are continuously cooling from high temperatures to room temperatures. Okay. And during this cooling process, we identify the start and end of transformations. For example, in this case again what I explained here is the transformation of austenite to ferrite, the begin transformation and end of austenite to ferrite transformation for an hypoelectrolyte steel. And then the moment the prototype ferrite formation finishes, then you would say have a pearlite formation, and this is pearlite start and pearlite end for this cooling rate. So now, if you look at this diagram, so apart from this ferrite and pearlite transformation, we also have various other lines. For example, we have a Bainite, and we have what you call the Martensite. And what are these? So we need to understand before going in detail about the CCD diagrams, and we look at what are the other possible microstructural features that can form when you are cooling continuously the austenite to room temperatures. Okay. So for that, we will first look at the morphology of these two phases. For example, Martensite Bainite, and this figure shows the other phases that may also form while cooling the austenite continuously to room temperature. So this is a typical microstructure of what you call as Martensite, and this is a microstructure of Bainite, what you see over here in the right hand side, right. So the formation mechanism of Bainite and Martensite is slightly different from the pearlite formation mechanism, right. So in the pearlite formation mechanism, so as I already explained, when austenite which has a carbon concentration less than prototype less than eutectide composition, you would first nucleate ferrite, and then ferrite, once it forms, it start ejecting carbon to the untransformed austenite, and that austenite transform to pearlite upon reaching the eutectide composition. So, then pearlite formation, if you want to understand, it's clearly you can refer this figure where we have the austenite when it cooled or when it transforming to pearlite, the ferrite first nucleates at the grind boundaries. As already explained, the carbon concentration of ferrite is always less than the carbon concentration of austenite. So, the moment ferrite forms, it has to reject carbon to the untransformed austenite or regions adjoining to the ferrite. So, the carbon goes away from ferrite to austenite. The moment you have a segregation of carbon sufficiently reached, you would start precipitating cementite. Okay. So, subsequently this austenite can grow, this ferrite can grow by consuming austenite, and during this process the ferrite rejects carbon and to adjoining regions and forming cementite lamellars, ferrite cementite lamellars as explained in this figure. And this happens you can say in close to equilibrium when you do not have high cooling rates as well as not high alloying elements. If you had a high amount of alloying elements, for example manganese, chromium, silicon, you may and with a slightly increasing cooling rate than you use it for pearlite formation, the morphology of the ferrite lamellars that you form in pearlite changes into somewhat acicular. Acicular means nothing but shape what is actually shown over here. The actual formation mechanism is similar to pearlite mechanisms driven by the carbon diffusion. Here what you see over here is the explanation about the Bainite formation. So, you have supersaturated the austenite. Okay. So, when you cool this austenite to room temperature, the carbon atom migrates from the ferrite to the adjoining austenite. Upon enrichment, you form a cementite at the interferrite regions. As I will explain, the mechanism is similar to pearlite formation mechanism. So, only thing is in this case the shape of the ferrite laths that form, they are not as uniform as you see over in pearlite formation, and you will have acicular structure. So, when the temperature is decreased even further, the carbon migration from ferrite is retarded because of the low diffusion rate of carbon from the ferrite to austenite. You may end up trapping some carbon atoms in the ferrite lath itself, and ultimately this ferrite upon segregation can also precipitate iron carbides, cementite, in the ferrite lath itself. Okay. And based on these formation mechanisms, and we can form two type of bainites, either what you call as an upper bainite, where you have a partitioning of carbon completely from the formed ferrite into cementite, into the adjoining the austenite, and end up nucleating cementite between the two interlath ferrite, or you may also end up precipitating the iron carbides inside the lath itself and some amount of the interlath cementite as well. And based on the morphology, so we term the structure as an upper bainite or a lower bainite. Generally upper bainite forms at slightly higher temperatures than the lower bainite, and because of this temperature difference we are also suppressing the carbon partitioning, complete carbon partitioning from the formed ferrite to the adjoining regions. Okay. So, with that we like to summarize what you have learned so far. So, we looked at the basic iron carbon system. So, what are the importance of the various lines you see in the phase diagrams. So, we looked at the regions that are interesting for us in this course. So, we looked at the octide compositions, the carbon in austenite and carbon in ferrite lines. Okay. So, what are the possible phases that can form in under equilibrium conditions when you cool, when you are transforming austenite to room temperatures. And so, we looked at the continuous cooling transformation diagrams. We looked at the formation of pearlite from austenite, how the carbon diffusion from ferrite to austenite, drives the transformation of Pearlite, and upon adding other alloying elements and increasing cooling rates, you also change the morphology of ferrite laths that are forming, which actually lead to the formation of Bainite. And Bainite can form in two ways. One by complete diffusion of carbon from the ferrite laths and forming interlath cementite or iron carbide, which is known as upper Bainite. And in lower Bainite, you also nucleate cementite inside ferrite laths. Thereby, the structure changes from a complete interlath cementite and ferrite structure into cementite inside the ferrite laths, as well as some amount of cementite in between laths as well. And this structure is known as lower Bainite.